The sky above you is not empty. It never was. What most people experience as a dark, featureless ceiling, a passive backdrop for city lights and morning clouds, is in reality a dynamic, ever-shifting theater governed by orbital mechanics, nuclear physics, and the raw gravitational choreography of bodies so massive they warp the very geometry of space around them. The night sky is not a painting. It is a live transmission from the universe itself, and in the year 2026, that transmission will carry signals unlike anything most living humans have ever witnessed, 9 of them specifically, not metaphors, not simulations, real phenomena, some so statistically rare that the last time they occurred, the Roman Empire was still a functioning state. Others so geometrically precise that astronomers need centuries of orbital data just to predict them to within a single hour. A few of them will be visible to the naked eye, requiring nothing more than clear skies and a willingness to stand still and look up. Others will demand binoculars or a modest telescope, or simply the knowledge of exactly where to point your gaze at exactly the right moment. What makes 2026 extraordinary is not any single event in isolation. It is the convergence, the stacking of phenomena across a 12-month window in ways that orbital mathematics did not have to arrange so generously. They simply fall this way. The planets move along their paths with complete indifference to human calendars, and yet this particular year, their geometry produces a catalog that professional astronomers have been anticipating with quiet intensity for well over a decade. So what are these 9 things? Before we get there, we need to understand what rare actually means when spoken by an astrophysicist, because it does not mean what most people assume it does. When a geologist calls something rare, they might mean it occurs once every 1,000 years. When a biologist calls a species rare, they might mean fewer than 10,000 individuals remain on Earth. Rarity in astronomy operates on a different scale entirely. An event that recurs every 130 years is, in astronomical terms, practically a routine occurrence. Some of the phenomena on this list have not been observed from Earth's surface in over 2 centuries. One of them, in its specific configuration, has never been recorded by any living human being. To be born in 2026 and grow to old age without seeing it again would not be unusual. It would be expected. That is the scale we are working with. To understand why rare celestial events are rare, you need to start with the fundamental architecture of our solar system. 8 planets orbit the Sun along paths that are not perfectly circular. They are ellipses, slightly elongated loops whose specific shape was determined by the chaotic conditions of the solar nebula 4.5 billion years ago. Each planet orbits at a different speed, governed by one of the most elegant relationships in all of science. The further a planet sits from the Sun, the slower it moves. Earth travels at roughly 29.5 kilometers per second. Jupiter, 5 times further out, moves at only 13 kilometers per second. Saturn, nearly 10 times the Earth-Sun distance, crawls along at just under 10 kilometers per second. To put that into human terms, if Earth were a runner completing a 400-meter track in 1 year, Jupiter would be finishing the same track in nearly 12 years, and Saturn would need over 29 years to cross the finish line. These different speeds mean that the geometric relationships between planets, the angles they form, the alignments they create, the positions they occupy relative to Earth and to each other, are always shifting. Most configurations resolve quickly and recur frequently, but certain combinations require multiple planets to be simultaneously positioned in very specific sectors of their orbits, and because those orbits have different periods, the mathematics of repetition becomes extraordinarily unforgiving. You might wait a lifetime. You might wait several. 2026 happens to be a year when several of those waiting periods end simultaneously. The moon is the most familiar object in the night sky, and most people believe they understand it reasonably well. They know it waxes and wanes over roughly 29.5 days. They know it occasionally turns red during a lunar eclipse. What most people do not fully appreciate is the extraordinary precision of the geometry required to produce even the most common lunar events, and how profoundly that geometry shifts when we move from common events to rare ones. The moon's orbit around Earth is tilted roughly 5 degrees relative to Earth's orbit around the sun. That 5-degree tilt is the reason we do not have a solar eclipse every single month. If the moon's orbit were perfectly aligned with the ecliptic, the plane of Earth's orbit, the moon would block the sun like clockwork, every 29.5 days without exception. Instead, most new moons pass slightly above or below the sun from Earth's perspective, invisible and harmless, their shadows sweeping through empty space tens of thousands of kilometers from our surface. For a total solar eclipse to occur, three things must align with near-perfect precision. The moon must be at new phase, it must be near one of the 2 points in its orbit where it crosses the ecliptic plane, and the geometry of distances must place the moon close enough to Earth that its apparent size in our sky very nearly matches the apparent size of the sun. The sun is 400 times wider than the moon. The moon is, on average, 400 times closer. That relationship, almost certainly a coincidence of orbital mechanics, not any grand design, is what makes total solar eclipses possible at all. And that relationship is slowly changing. The moon drifts about 3.8 centimeters further from Earth every year. In the deep future, it will be too far away to fully cover the sun, and total solar eclipses will become geometrically impossible. We live in a window, a specific finite window in the lifespan of this planet when total solar eclipses can occur. In 2026, that window produces something remarkable. On August 12th, a total solar eclipse will cross the North Atlantic, touching Greenland, Iceland, and northern Spain before sweeping across the Iberian Peninsula in a path of totality, roughly 160 kilometers wide. For observers in cities like Palma de Mallorca, the daytime sky will darken to a deep twilight. The temperature will drop perceptibly, birds will fall silent. The solar corona, the sun's outer atmosphere, a structure so faint it is normally drowned out by the photosphere's brilliance, will become visible to the naked eye as a ghostly white halo extending several solar radii into space. Stars will appear in the middle of the day. Venus, if properly positioned, may be visible as a bright point of light in a darkened afternoon sky. Totality, for those in the optimal path, will last up to 2 minutes and 18 seconds. 2 minutes and 18 seconds sounds brief, but for every astronomer who has stood beneath the shadow of the moon and watched the corona materialize out of a vanished sun, time inside totality operates by different rules. It is not a visual spectacle in the ordinary sense. It is, by consistent account across centuries of observation, a physical confrontation with the scale of the solar system. You are not watching a photograph. You are standing on a moving planet as a moving moon casts its shadow across a curved surface at over 1,700 kilometers per hour, briefly pulling you into darkness in the middle of the day. The last total solar eclipse visible from mainland Western Europe occurred in August 1999, tracking across Cornwall, France, and Central Europe. Before that, you would need to go back to June 1927 for a path across the British Isles. For millions of people in Spain and Portugal, the eclipse of 2026 will be the first total solar eclipse they will ever witness from their home country. For some, it will be the only one in their lifetimes. That is one of the 9. The moon does not reveal all its complexity in a single event. Its orbit shifts, precesses, and oscillates over timescales far longer than a human life. Right now, and for the next 2 years, the moon is in a phase of its 18.6-year nodal cycle known as a lunar standstill. During this period, the moon's monthly arc across the sky reaches its most extreme northern and southern limits, rising and setting at points along the horizon far outside its average range. Ancient megalithic structures like Callanish in Scotland and Chimney Rock in Colorado appear to have been deliberately aligned to the major lunar standstill. The last one occurred in 2006. The next one peaks in 2025 and 2026. What this means in practice is that during this 2-year window, the full moon will rise and set at positions on the horizon that it will not reach again for nearly 19 years. For observers in northern latitudes, the midwinter full moon of 2025 and 26 will skim so close to the horizon during its low point months that it creates an atmospheric optical phenomenon rarely captured on camera. A moonrise compressed and distorted by thick layers of atmosphere into an enormous, flattened, amber disk hovering just above the Earth's edge. 2 events already. 7 remain. And the most geometrically improbable of all, the one that no living human has ever witnessed in person, is still coming. 6 planets, simultaneously visible in the same sky, strung across the ecliptic like a string of lights pulled taut from one horizon to the other. On the evening of February 28, 2026, anyone standing under a reasonably dark sky shortly after sunset could look west and trace a line. Mercury close to the horizon, then Venus blazing above it, then Jupiter, then Saturn, then the ice giants Uranus and Neptune fading at the edge of naked-eye visibility, all arranged along the same great arc that the sun traces daily across the sky. 6 worlds, each one a distinct physical body with its own atmosphere, its own gravity, its own geological or meteorological history. All of them visible, simultaneously, from a single human vantage point on the surface of a 7th world. This is not magic. It is the direct consequence of where those planets formed and why they formed there. 4.5 billion years ago, the disk of gas and dust that surrounded the young sun was not a sphere. It was flat. Gravitational forces and angular momentum from the original collapsing nebula ensured that most of the material settled into a thin plane, and it was within that plane that the planets assembled from colliding clumps of rock, ice, and gas. The result is that all 8 major planets orbit the sun within a few degrees of the same plane. When we observe them from Earth, they appear to move along a narrow band of sky, the ecliptic, rather than scattered randomly across the celestial sphere. That shared geometry is the reason a planetary parade is even possible. The planets cannot help but align roughly along that line. The real question is only ever how many are simultaneously above the horizon at a given moment from a given place on Earth. For 6 to appear at once requires a particular configuration of orbital positions that does not repeat on any convenient schedule. The February 28th alignment of 2026 places Mercury, Venus, Jupiter, and Saturn in positions where all 4 are naked-eye objects. Venus is unmistakable, the brightest natural object in the night sky after the moon, reaching negative 4.5 magnitude during its apparitions, bright enough to cast a faint shadow on a white surface in complete darkness. Jupiter rivals it from further out, sitting at roughly negative 2 magnitude at the time of the parade. Saturn glows steadily at around 1.2 magnitude, fainter but absolutely recognizable by the absence of any twinkle, the hallmark of a planet whose disk, however small it appears to the naked eye, is just wide enough to suppress the atmospheric scintillation that makes true stars shimmer. Then there are Uranus and Neptune. These 2 planets occupy a strange middle ground in the history of astronomy, one just barely visible to the naked eye under ideal conditions, the other definitively not. Uranus sits at approximately 5.9 magnitude during this alignment, theoretically within the range of human vision but requiring dark skies and deliberate effort. Neptune, at 7.8 magnitude, is fully beyond unaided sight, requiring at minimum a pair of binoculars. Their inclusion in a planetary parade is therefore partly a matter of definition. Whether you count them depends on whether you require naked-eye visibility or simply presence above the horizon. But their physical reality in that strip of sky is unaffected by the debate. What the naked-eye observer experiences on that February evening is something deeply ancient. Before the invention of the telescope, every civilization that practiced systematic sky observation, Babylonian, Egyptian, Greek, Chinese, Mayan, tracked exactly these 5 naked-eye planets, and only these 5: Mercury, Venus, Mars, Jupiter, Saturn. They were not called planets in the modern sense. The Greeks called them planets, meaning wanderers, because unlike the fixed stars, they moved against the stellar background from night to night. Generations of observers spent decades cataloging those movements, trying to understand the pattern, the regularity, the underlying logic. The data they accumulated, laboriously recorded on clay tablets and papyrus, became the empirical foundation upon which modern orbital mechanics was eventually built. When Nicholas Copernicus published De Revolutionibus Orbium Coelestium in 1543, he was not inventing a new model from scratch. He was reinterpreting centuries of planetary position data, including those 5 wanderers, through a new geometric framework that placed the Sun, rather than the Earth, at the center of the system. The heliocentric model was not immediately embraced. It faced resistance not primarily for religious reasons, but for a specific and entirely rational scientific objection. If the Earth moved around the Sun, then nearby stars should show a detectable shift in apparent position, what astronomers call parallax, relative to more distant background stars, as Earth moved from one side of its orbit to the other. No one could detect it. Copernicus correctly surmised that the stars were simply too far away for the parallax to be measurable with instruments of his era. He was right. Stellar parallax was finally measured directly for the first time in 1838 by Friedrich Bessel, who detected a shift of just 0.3 of an arcsecond for the star 61 Cygni, a star roughly 11 light-years away. 0.3 of an arcsecond, that is approximately 1/12,000th of the apparent diameter of the full moon. The precision required to detect that shift in 1838 using telescopes aimed at a star 11 light-years distant is worth pausing on. 11 light-years is approximately 104 trillion kilometers. To put that in terrestrial terms, if the Sun were the size of a period at the end of a sentence, and Earth were a grain of fine sand roughly 11 centimeters away, then 61 Cygni would be another period sitting approximately 3 kilometers away. Bessel measured the apparent angular shift of that period from a grain of sand moving on a nearly circular path to within fractions of an arcsecond using a refractor telescope in Königsberg. The measurement confirmed heliocentrism with direct geometric evidence and placed humanity's first physical ruler on interstellar distance. That moment, 1838, is the fulcrum on which the modern understanding of the cosmos balances. Now return to the February parade. 6 planets in one sky. The 2 ice giants, Uranus and Neptune, were not part of any ancient observer's catalog. William Herschel discovered Uranus in 1781, initially reporting it as a comet. Before orbital calculations made the truth undeniable, it moved too slowly and too smoothly for a comet. It was a world. Neptune was found mathematically before it was found optically. In 1846, the French mathematician Urbain Le Verrier analyzed the orbital perturbations of Uranus, tiny wobbles in its predicted path caused by gravitational tugging from an unknown body, and calculated where that body must be. He sent his prediction to Johann Galle at the Berlin Observatory. Galle pointed his telescope to the predicted coordinates on September 23, 1846. Neptune was there, within 1 degree of Le Verrier's prediction. It had been found by pure mathematics, before a single human eye had ever knowingly rested upon it. That is the nature of orbital mechanics. It is not approximate. Given accurate initial conditions and sufficient computational precision, the gravitational equations of classical mechanics can predict planetary positions centuries into the future with extraordinary fidelity. This is exactly how every date in 2026's astronomical calendar was established, not by observation after the fact, but by calculation years and decades in advance. The total lunar eclipse of March 3, 2026, was known to professional astronomers long before the 21st century began. A total lunar eclipse is geometrically simpler than a solar eclipse, but no less visually dramatic. The geometry requires the Sun, Earth, and Moon to align closely enough that the Moon passes through Earth's umbral shadow, the central, darkest cone of shadow where direct sunlight is fully blocked. The Moon does not disappear during totality. Instead, it turns red. The reason is physics, not mystery. Earth's atmosphere refracts and scatters sunlight around the planet's limb, bending red wavelengths inward into the shadow cone while scattering shorter blue wavelengths away. The effect is equivalent to projecting every sunrise and sunset on Earth simultaneously onto the face of the Moon. The color and intensity of that red, ranging from pale copper to deep blood crimson to near charcoal, depends on the state of Earth's atmosphere at the moment of totality. Active volcanic eruptions can darken the Moon to near invisibility during totality by loading the stratosphere with sulfate aerosols that reduce the refracted light reaching the lunar surface. During the totality following the eruption of Mount Pinatubo in 1991, some observers reported the Moon nearly vanishing from the sky. The March 3rd eclipse of 2026 will be visible across the Americas, Europe, and Africa, totality lasting approximately 1 hour and 2 minutes. 1 hour. The moon sitting inside Earth's shadow, turning colors that no body outside a planetary atmosphere could produce. The physics of light and air, projected across 384,000 kilometers of space onto 4.5 billion-year-old rock. What drives the precision of these predictions is a body of physics assembled over roughly 3 centuries, beginning in earnest with Isaac Newton's Principia Mathematica in 1687. Newton's law of universal gravitation states that every body in the universe attracts every other body with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This single relationship, combined with his 3 laws of motion, is sufficient to compute the orbit of any body in the solar system to extraordinary accuracy, provided you know its position and velocity at some initial moment. Every eclipse prediction, every planetary conjunction date, every perihelion passage, every opposition, all of it flows directly from these equations, refined over 3 centuries by the work of Laplace, Lagrange, Gauss, Poincaré, and eventually the computational power of electronic computers. The equations do not care about human calendars or human significance. They are indifferent. And yet they have arranged 2026 into a year of convergence so dense that professional astronomers and amateur observers worldwide are treating it as a once-in-a-generation observing window. There is still one event on the list that none of those equations fully prepared the scientific community to understand when it was first observed. An object that appeared from deep in the outer solar system, following a trajectory that no known comet had traced before, emitting signals in wavelengths that challenged every existing model of cometary composition. Its designation is C2025-R3. It was discovered less than a year ago, and in late April of 2026, it passed its closest point to Earth. What it is, and what it may be telling us about the far outer reaches of the solar system, is where the real science begins to get unsettling. A comet is not a dirty snowball. That phrase, dirty snowball, entered popular astronomy vocabulary in 1950 when Harvard astronomer Fred Whipple published his model describing cometary nuclei as compact bodies of frozen water, carbon dioxide, ammonia, and dust. The model was revolutionary for its time and broadly correct in its framework. But 5 decades of spacecraft encounters, spectroscopic analysis, and infrared observation have complicated the picture to the point where the original metaphor now obscures more than it reveals. The nucleus of Comet Halley, imaged up close by the European Space Agency's Giotto probe in 1986, was not a bright, reflective ball of ice. It was one of the darkest objects in the solar system. A lumpy, irregular body roughly 15 kilometers long and 8 kilometers wide, its surface blacker than coal, reflecting only about 4% of incoming sunlight. Most of its surface was inert, dead crust. Only a small fraction of the surface, where sunlight penetrated the dark coating and reached subsurface ices, produced the jets of gas and dust that form the visible coma and tail. The nucleus of a comet is a time capsule. Not metaphorically, literally. The material that makes up cometary nuclei formed in the outer solar system during the earliest phases of solar system assembly, at temperatures so low that volatile compounds that would evaporate instantly in the inner solar system were preserved in solid form. Water ice, carbon monoxide, carbon dioxide, methanol, hydrogen cyanide, formaldehyde, compounds that date back 4.5 billion years, preserved in a deep freeze at the edge of the solar system, untouched by the geological and thermal processing that reshape the inner planets beyond recognition. When a comet falls inward toward the sun and begins to sublimate, it is releasing material that formed before Earth existed. The gas and dust streaming away in the comet's tail were locked in that nucleus since before the first continent rose above a primordial ocean on this planet. C2025-R3 was first detected in September of 2025 by an automated sky survey program flagged as a fast-moving point of light in the outer solar system. Initial orbital calculations immediately produced something unusual. The trajectory was hyperbolic. Not slightly hyperbolic, significantly so. Its orbital eccentricity was calculated above 1.0, meaning it was not gravitationally bound to the sun. It was passing through the solar system on a one-way trajectory, arriving from interstellar space and destined to return to it. This is the second such object ever confirmed. The first was Oumuamua, detected in October 2017 by the Pan-STARRS Survey Telescope in Hawaii. Oumuamua arrived from the direction of the constellation Lyra, moving at roughly 26 kilometers per second relative to the Sun at infinity, a speed far exceeding solar escape velocity, definitively establishing its interstellar origin. What made Oumuamua deeply strange was not merely its trajectory. It was the shape inferred from its light curve, the periodic variation in brightness as it rotated. The amplitude of that variation was extraordinary, implying an object with an aspect ratio somewhere between 5:1 and 10:1, either an extremely elongated cylinder or a flat, disc-like geometry. No known solar system body showed anything like it. And then, as it accelerated away from the Sun, it exhibited non-gravitational acceleration, a gentle but measurable push beyond what solar gravity alone could account for. Outgassing from sublimating ices, the same process that produces cometary tails, was the most natural explanation, but no coma, no tail, and no detectable outgassing signature was observed. The acceleration was real. Its source remained unresolved. The scientific community published dozens of papers. Explanations ranged from radiation pressure on an unusually thin, flat structure to exotic suggestions that generated public attention far disproportionate to their scientific probability. The honest answer, which the majority of researchers settled on, was simply, we did not observe it long enough, and our instruments were not sensitive enough to determine its composition or the precise mechanism of its anomalous acceleration. Oumuamua was gone before we understood it. C2025R3 is different in one critical respect. It was detected early enough. When Oumuamua was found, it had already passed its closest point to the Sun, perihelion, and was accelerating outward. Astronomers had weeks, not months, to observe it before it faded below detectability. C2025R3 was spotted while still in the outer solar system, months before perihelion, providing a window of observation that Oumuamua never offered. Spectroscopic analysis during its inbound journey detected clear signatures of molecular outgassing, carbon monoxide and carbon dioxide emissions consistent with a cometary nucleus of roughly interstellar composition. It had a detectable coma. It behaved in this respect more like the second confirmed interstellar object, Borisov, detected in 2019, which was definitively cometary and showed outgassing consistent with solar system comets. But C2025R3's non-gravitational acceleration profile, measured with high precision as it approached perihelion, does not match standard cometary jet models at the level of precision now available. The discrepancy is small, but it is there, and it is consistent across multiple independent reduction pipelines. Whether it represents an unusual composition, a highly anisotropic outgassing geometry, or something else entirely, is the subject of active, unresolved analysis. Now consider what interstellar space actually is, and what it means for an object to have crossed it. The nearest star system to the Sun is Alpha Centauri, at a distance of approximately 4.2 light-years, roughly 40 trillion kilometers. Light, traveling at 300,000 kilometers per second, takes 4.2 years to cover that distance. A spacecraft traveling at the speed of the New Horizons probe, approximately 16 kilometers per second, the fastest human-made object currently leaving the solar system, would require roughly 78,000 years to reach Alpha Centauri. C 2025R3, traveling at its measured interstellar velocity, would have taken a comparable timescale to cross a similar distance. The implication is that this object was ejected from another star system tens of thousands to hundreds of thousands of years ago, and has been traveling through interstellar space, in complete darkness, at temperatures near absolute zero, approximately minus 270 degrees Celsius, for all of recorded human history, and then some, before its gravitational encounter with the Sun brought it briefly into our skies. Absolute zero is minus 273.15 degrees Celsius. The cosmic microwave background radiation, the thermal remnant of the Big Bang, the lowest ambient temperature in the observable universe, sits at approximately 2.7 Kelvin, or minus 270.45 degrees Celsius. The surface of an interstellar object in deep space, far from any star, approaches but never quite reaches absolute zero because it is gently warmed by this background radiation field, the universe's own residual heat signature from an event 13.8 billion years ago. That context rewrites what you are looking at when you observe a comet. The physics of cometary tails contains a detail that most casual sky observers do not realize. A comet's tail does not stream behind it the way exhaust trails behind a jet aircraft. A comet's tail always points away from the sun, regardless of the comet's direction of travel. When a comet is moving away from the sun, its tail precedes it. The reason is solar radiation pressure and the solar wind, a continuous stream of charged particles flowing outward from the sun at roughly 400 to 800 kilometers per second, sweeping cometary material away from the sun's direction regardless of the comet's own velocity vector. Most bright comets actually develop two distinct tails: a dust tail, which curves gently and reflects sunlight in a warm yellowish-white color, and an ion tail, also called a plasma tail, which is straighter, bluer, and consists of ionized gas molecules being driven away by the solar wind's magnetic field at speeds far exceeding the dust particles. The ion tail points almost precisely anti-sunward. The dust tail curves away from it by varying degrees depending on the relative velocities of the particles and the geometry of the comet's orbit. During the closest approach of C 2025 R3 in late April 2026, roughly 1 astronomical unit from Earth, meaning approximately the same distance that separates Earth from the Sun, or 150 million kilometers, observers in the southern hemisphere with binoculars reported the ion tail as a faint blue-green streak extending several degrees across the sky. Several degrees of arc corresponds at that distance to a physical structure tens of millions of kilometers in length. A tail of ionized gas tens of millions of kilometers long, grown from a nucleus that may be only a few kilometers across, is itself a statement about the scale of the forces involved. The Sun, at 150 million kilometers, is still powerful enough to strip molecules from a nucleus and accelerate them into a structure larger than the distance from the Sun to Mercury. The thermal physics governing what happens to cometary ices as solar distance decreases follows a well-understood progression. At distances beyond roughly 5 astronomical units, Jupiter's orbital neighborhood, water ice is stable on a cometary surface. The solar flux is too weak to sublimate it. Carbon monoxide and carbon dioxide, with their lower sublimation temperatures, begin outgassing at much greater distances. This is why newly detected comets entering the inner solar system for the first time often show unexpected activity at large distances from the Sun. Their more volatile ices, untouched on previous apparitions or on their very first approach, begin vaporizing while the comet is still in the outer solar system. As solar distance decreases below roughly 2 to 3 astronomical units, water ice sublimation accelerates dramatically, and the coma expands. Below 1 astronomical unit, the nucleus surface temperature in directly illuminated areas can reach several hundred Kelvin, and the outgassing rate peaks. C 2025 R3 passed perihelion, its closest point to the Sun, at approximately 0.8 astronomical units, putting it inside Earth's orbit. At that distance, whatever surface ices were accessible had been sublimating aggressively for weeks. The infrared and spectroscopic data collected during this period by ground-based observatories and the James Webb Space Telescope represent the most detailed dataset ever obtained for an interstellar object at perihelion. The James Webb Space Telescope is not a conventional optical instrument. Its primary mirror, composed of 18 gold-coated beryllium hexagonal segments, spans 6.5 meters in diameter, more than 2.5 times the collecting area of the Hubble Space Telescope. It operates primarily in the near-infrared and mid-infrared wavelength ranges that penetrate dust and reveal molecular emission lines invisible to optical telescopes. Positioned at the second Lagrange point, roughly 1.5 million kilometers from Earth in the direction away from the Sun, it operates at a temperature of approximately 40 Kelvin, kept cold by a 5-layer sunshield the size of a tennis court. At 40 Kelvin, its own thermal emission does not contaminate its measurements in the infrared bands it uses most. Pointing that instrument at an interstellar comet during perihelion passage is, in terms of scientific opportunity, without historical precedent. The molecular fingerprints embedded in the spectroscopic data from C2025R3 will be analyzed for years after the object has long departed. They carry information about the chemistry of a disk of gas and dust that orbited another star, stellar chemistry, planetary formation conditions, isotopic ratios, preserved in a nucleus traveling between the stars for timescales that overlap with the entire span of human civilization. What those spectra are beginning to suggest about the isotopic composition of the water ice in that nucleus is not what standard models of solar system cometary chemistry would predict. And that discrepancy, small, provisional, but stubbornly present in the preliminary reduction, connects directly to a question that has sat at the edge of planetary science for 4 decades. Whether the water in Earth's oceans came, at least in part, from exactly these kinds of objects. The question of where Earth's water came from is not settled science. That statement surprises most people because water feels like the most fundamental feature of this planet. The thing that defines it visually from space, the thing that makes it biologically active, the thing that fills 71% of its surface to an average depth of 3,688 meters. The total volume of water on Earth is approximately 1.38 billion cubic kilometers. It seems impossible that we would not know with certainty where all of it came from. The difficulty is deep time. Earth formed approximately 4.54 billion years ago from the collision and accretion of rocky bodies in the inner solar system. At that distance from the Sun, roughly 1 astronomical unit, the temperature of the protoplanetary disk during Earth's formation was too high for water ice to condense stably onto solid particles. The region beyond roughly 2.7 astronomical units is called the frost line, or snow line, the distance at which water vapor could condense into ice grains and be incorporated directly into forming bodies. Earth formed well inside that line. The rock and metal that built our planet was, in its original composition, largely dry. And yet the oceans exist. They have existed in some form for at least 4 billion years. We know this from ancient zircon crystals found in Western Australia, the Jack Hills zircons, some dated to 4.4 billion years old, whose oxygen isotope ratios are consistent with formation in the presence of liquid water. Earth had surface water within 150 million years of its formation. Somehow, water was delivered to a planet that formed dry. 3 delivery mechanisms have been seriously proposed and studied. The first is adsorption, the possibility that rocky materials forming in the inner solar system retained trace amounts of water chemically bonded to mineral surfaces, sufficient in aggregate to account for Earth's oceans. The second is delivery by asteroids, specifically the carbonaceous chondrite meteorites, which contain between 3 and 22% water by mass locked in hydrated silicate minerals. The third is delivery by comets, icy bodies from the outer solar system diverted inward by gravitational perturbations, crashing into the early Earth and depositing their volatile inventory. The key to distinguishing these sources is isotopic chemistry. Water is not a single molecule. It comes in variants depending on which isotopes of hydrogen and oxygen compose it. The most useful diagnostic is the ratio of deuterium, heavy hydrogen, with 1 proton and 1 neutron in its nucleus, to ordinary hydrogen, which has only a proton. This ratio, written as DH, varies predictably depending on where in the solar system material formed. Water that condensed in the cold outer solar system, far from the Sun, tends to have a higher DH ratio than water that formed or was processed closer to the Sun. Earth's ocean water has a DH ratio of approximately 1.56 times 10 to the negative 4. When astronomers first measured the DH ratio of water ice in comets from the Oort cloud, the distant spherical reservoir of comets that extends from roughly 2,000 to 100,000 astronomical units from the Sun, the values came back approximately twice Earth's ocean ratio. Halley's Comet, Comet Hyakutake, Comet Hale-Bopp, all of them showed DH ratios roughly double the terrestrial standard. For nearly 2 decades, this single measurement effectively ruled comets out as the primary source of Earth's oceans. The numbers did not match. Then, in 2011, the European Space Agency's Herschel Space Observatory measured the DH ratio of Comet Hartley 2, a Jupiter family comet originating from the Kuiper belt rather than the Oort cloud. The result was extraordinary. Hartley 2's DH ratio matched Earth's ocean water almost exactly. One measurement from one comet of a different dynamical family than the previously measured Oort cloud comets, and suddenly the door that had been closed for 20 years swung back open. The scientific community did not immediately revise the consensus. One measurement is not a consensus, but it was the trigger for a cascade of follow-up observations that have progressively complicated the simple picture. Jupiter family comets, which originate in the Kuiper belt, the disk of icy bodies extending from Neptune's orbit at 30 astronomical units out to roughly 50 astronomical units, appeared to have systematically different DH ratios than Oort cloud comets. The reason, theoretically, relates to the temperature gradient in the original solar nebula at different distances and the chemical processing of ices by cosmic ray irradiation over billions of years in different reservoir environments. When ESA's Rosetta spacecraft arrived at Comet 67P Churyumov-Gerasimenko in 2014 and began its extraordinary 26-month orbital escort, the first time a spacecraft had ever orbited a cometary nucleus, one of its primary scientific instruments, the Rosina mass spectrometer, measured the DH ratio of water vapor streaming directly from the nucleus surface. The result placed 67P firmly back in the high DH category, approximately 3 times the terrestrial ocean value. 67P is a Jupiter family comet from the same dynamical population as Hartley 2. And yet its DH ratio contradicted Hartley 2's entirely. The Rosetta result did not invalidate the Hartley 2 measurement. It revealed that the DH ratio is not uniform even within the same comet family. Different comets, even from the same source reservoir, can have dramatically different isotopic water compositions. This implies that the original distribution of DH ratios across the outer solar system was not uniform, that the chemical history of individual nuclei matters, and that no single comet can serve as a representative sample for its entire dynamical population. See 2025 R3, as an interstellar object, a body that did not originate anywhere in our solar system, carries DH information from an entirely different stellar environment. If its water ice can be accurately characterized, it represents a data point outside the entire framework of solar system isotope geochemistry. The preliminary JWST spectroscopic data released in early 2026, before full peer review, suggested a DH ratio measurably different from both Earth's oceans and from any solar system comet measured to date. The value, if confirmed, falls between Oort cloud comets and the terrestrial standard, neither a match nor a complete mismatch. What that means is still being worked out. But the broader implication has not escaped the planetary science community. If interstellar objects passing through the solar system carry water ice with DH ratios that partially overlap the terrestrial range, and if the early solar system was bombarded by interstellar objects during the period of heavy planetary accretion, a period when the solar system's own Oort cloud was still forming and the gravitational environment was far more chaotic than today, then the delivery of water to early Earth was potentially not a purely internal solar system affair. The late heavy bombardment, a period roughly 3.9 billion years ago, during which the inner planets were subjected to a dramatically elevated rate of impact by asteroids and comets, is preserved in the lunar cratering record. The Moon, geologically inactive and lacking the erosional processes that have resurfaced Earth, still carries the scars of this bombardment in the form of ancient impact basins visible through any telescope. The South Pole Aitken Basin on the lunar far side is roughly 2,500 kilometers across and 13 kilometers deep, one of the largest confirmed impact craters in the solar system, dating from this era. These impacts were not gentle. They delivered enormous quantities of volatile material to the inner solar system, including water, at the very time when Earth's surface conditions were becoming compatible with the retention of liquid water. The current working model, supported by the broadest cross-section of evidence, is that Earth's water arrived from multiple sources at different times, some from hydrated asteroids in the main belt, some from comets. Possibly some retained from the original rocky material of accretion. No single source dominates the entire budget cleanly. The carbonaceous chondrite connection is currently the strongest supported pathway for the bulk of Earth's water because DH ratios from the Ci and Cm chondrite classes, the most water-rich meteorite types, fall much closer to the terrestrial ocean value than do Oort cloud comets. But the arrival of C 2025 R3 has introduced a variable that no model had been built to accommodate. A body from outside the solar system entirely, observed at perihelion with the most sensitive spectrographs ever built, carrying volatile chemistry that did not originate in any star system we have yet catalogued. The James Webb Space Telescope's NIR-SPEC instrument, the near-infrared spectrograph, operates across wavelengths from 0.6 to 5.3 microns and can simultaneously record spectra from multiple objects at resolving powers sufficient to distinguish individual molecular emission lines separated by fractions of a nanometer. During C 2025 R3's perihelion passage, NIR-SPEC was used to record detailed emission spectra of the coma at multiple epochs. The data showed unambiguous signatures of water vapor, carbon dioxide, carbon monoxide, and what appears to be a moderately strong signal from ethane, a molecule whose presence in cometary comae has been used as a tracer of the temperature history of the ices and the irradiation environment in which they formed. The ethane-to-water ratio in C 2025 R3's coma differs from the range observed in solar system comets by a margin that exceeds measurement uncertainty. It is not a radical difference, not a completely alien chemistry, but it is a consistent, statistically significant offset across multiple independent spectra taken at different times and with different instrument configurations. It reflects a formation environment with subtly different irradiation history, different temperature structure in the parent protoplanetary disk, or different elemental abundances in the star system from which this object originated. In short, the chemistry of another star's planetary system, encoded in the gas streaming off a nucleus a few kilometers wide, was directly measured by an instrument orbiting our own sun at 1.5 million kilometers from Earth in the spring of 2026. No human instrument had ever done that before. The accumulation of data from this object, still being reduced, still being subjected to peer review, is already reshaping the theoretical framework for how chemically diverse the galaxy's planetary formation environments might be. It is also quietly reopening the question of panspermia, not the science fiction version involving deliberate seeding or directed intelligence, but the stripped-down chemical version, the possibility that organic precursor molecules, or even more complex prebiotic compounds, could be transported between star systems in the nuclei of exactly these kinds of interstellar objects, deposited during close passages through inhabited or potentially habitable systems. The organic chemistry of comets is not speculative. The Rosetta mission's Rosina instrument detected over 400 distinct organic molecules in the coma of 67P, including glycine, the simplest amino acid, and phosphorus, an element essential to the backbone of DNA. Amino acids have been found in carbonaceous chondrite meteorites since the 1960s, including in the Murchison meteorite that fell in Australia in 1969, which contained over 90 different amino acids, the majority of which are not among the 20 used in terrestrial biology. Chemistry does not care about the boundaries we draw between biology and geology. At sufficiently cold temperatures and under the right ultraviolet irradiation conditions, simple molecules, water, carbon monoxide, ammonia, methanol, react on the surfaces of dust grains to form more complex organics. This process does not require life. It requires only chemistry, time, and the conditions that exist throughout the interstellar medium. An interstellar comet carries a record of that chemistry from another stellar environment across light years of space and delivers it, briefly, irreversibly, into the observable range of the best instruments our civilization has ever constructed. 2026 has given us, for only the second time in recorded history, a chance to read that record before it escapes into the dark. On the morning of August 12, 2026, the moon's shadow will touch the surface of the Atlantic Ocean at approximately 9:47 Universal Time, moving at over 2,000 kilometers per hour across open water before making landfall on the southwestern tip of Greenland. The shadow is not a gradual dimming. It has two components, distinct in their geometry and in what they produce on the ground. The penumbra, the outer partial shadow, spans thousands of kilometers and produces the partial eclipse experienced by observers across most of Western Europe and North Africa. Within it, the sun appears as a crescent, progressively narrowed as the moon's disk advances. But the umbra, the central shadow, The narrow cone where the moon fully blocks the solar photosphere is at most around 160 kilometers wide at its contact point with Earth's curved surface. To stand inside that cone is to experience something categorically different from a partial eclipse. It is a different phenomenon entirely, not a more extreme version of the same thing. The physics of what happens inside the umbral path during totality unfolds in a precise sequence governed entirely by orbital geometry. Several minutes before totality, the light quality changes in ways that photographic exposure meters register, but that the human eye processes as something subtly wrong. Color temperature shifts, shadows sharpen. The fraction of the sun's photosphere still visible, even as little as 1%, is sufficient to maintain daylight illumination at an elevated level because the photosphere is so luminous that 1% of it still outcompetes any artificial light source humans have constructed. This is why the transition from partial eclipse to totality is not gradual. It is a threshold. At the instant the last sliver of photosphere disappears behind the lunar limb, the light level drops by a factor of roughly 1 million, from full daylight to a twilight comparable to 10 to 20 minutes after sunset, in an interval measured in seconds. The human visual system evolved over millions of years under conditions where light transitions of that speed do not naturally occur, has no adequate response protocol. Observers who have experienced totality consistently describe a physical shock at that moment that no amount of prior knowledge or preparation eliminates. What appears in the sky at totality is the solar corona. The corona is the sun's outer atmosphere, a region of fully ionized plasma extending millions of kilometers from the solar surface. Its temperature is one of the most counterintuitive facts in all of solar physics. While the sun's visible surface, the photosphere, sits at approximately 5,778 Kelvin, the corona reaches temperatures between 1 million and 3 million Kelvin, and in active regions can exceed 10 million Kelvin. A stellar atmosphere that grows hotter as it moves further from the heat source is a direct violation of thermodynamic intuition. Heat does not flow from cold to hot. The corona should be cooler than the photosphere. It is not by a factor of several hundred, and the precise mechanism responsible, the coronal heating problem, has not been fully resolved despite decades of theoretical work and direct observation by spacecraft, including the Parker Solar Probe, which in 2021 became the first human-made object to fly through the solar corona itself. The corona is always there. It cannot be seen from Earth's surface during ordinary conditions because the photosphere's brilliance, roughly 500,000 times brighter than the full moon, scatters through the atmosphere and drowns the faint coronal emission entirely. The invention of the coronagraph in 1930 by the French astronomer Bernard Liot created an artificial occulting disk that blocks the photospheric disk inside a telescope, allowing continuous observation of the inner corona. But no coronagraph has ever replicated the full visual fidelity of a natural total solar eclipse. The sky during totality is darker than any coronagraph's field of view by orders of magnitude, and the spatial dynamic range of the corona visible to the naked eye, from the bright inner corona to the faint streamers extending several solar radii outward, exceeds what any instrument has fully captured in a single exposure. During the August 2026 eclipse, the sun will be near the peak of solar cycle 25. Solar activity follows an approximately 11-year cycle of rising and falling sunspot number, coronal complexity, and frequency of energetic events. Solar maximum for cycle 25 was reached in 2024 and 25, but the solar corona remains highly structured and active as the cycle begins its descent. At solar maximum, the corona does not display the relatively simple equatorially symmetrical streamer belt visible at solar minimum. Instead, it erupts in all directions: plumes, helmets, pseudo-streamers, and the swept-back signatures of recent coronal mass ejections radiating outward in a complex pattern that changes measurably from one eclipse to the next. The corona visible from Spain and Iceland on August 12th will not be the same corona any eclipse expedition measured in 2024 or 21 or any prior year. It is a snapshot of a specific moment in the sun's magnetic cycle. Astronomers will be deployed along the path of totality with narrowband hydrogen alpha and iron emission line filters, polarimetric cameras, and high-cadence imaging systems capable of capturing coronal dynamics at sub-second timescales. The 2 minutes and 18 seconds of totality at the center of the path represents roughly 138 seconds of irreplaceable data collected simultaneously from multiple ground stations, data that no space-based coronagraph can replicate. The path of totality crosses the Balearic Islands at approximately 10:22 Universal Time. Palma de Mallorca sits almost precisely on the central line, the axis of the umbral shadow where totality duration is longest and the shadow geometry is most symmetric. In the minutes before first contact, the moment the moon's disk first encroaches on the sun's limb, the temperature will be dropping measurably. Insects and birds respond to the dimming and cooling. These behavioral responses have been documented in the scientific literature across multiple eclipse events and represent genuine biological reactions to the change in light and temperature, not behavioral artifacts. As the partial phase deepens toward totality, shadow bands may appear, thin, rapidly moving alternating light and dark fringes that ripple across pale, flat surfaces seconds before and after totality. Their origin lies in atmospheric turbulence, acting as a lens on the light from the razor-thin crescent of photosphere just before it vanishes. They are unpredictable, not always present, dependent on atmospheric conditions, and have been observed and documented since at least 1842. Their exact physical mechanism has been debated. The current consensus attributes them primarily to the interference and refraction of coherent light from the thin solar crescent passing through turbulent refractive index variations in the lower atmosphere. 14 seconds before totality, the Baily's beads phenomenon occurs, as the moon's limb, not a smooth geometric circle but a topographically irregular surface of mountains, valleys, and crater rims, advances across the solar disk. The last remaining shafts of photospheric light pass through lunar valleys and emerge as a chain of brilliant points along the moon's edge. They are named for the English astronomer Francis Baily, who provided the first clear scientific description following the annular eclipse of May 15, 1836. In the final seconds before totality, the beads reduce to a single brilliant point, the diamond ring effect, as sunlight streams through one last lunar valley against the emerging corona. Then, that point extinguishes. Totality begins. Simultaneously with the onset of totality, the chromosphere, the thin layer of solar atmosphere just above the photosphere, roughly 2,000 kilometers thick, becomes visible as a narrow arc of vivid pinkish red at the moon's limb. The color comes from hydrogen alpha emission at a wavelength of 656.3 nanometers. Ionized hydrogen in the chromosphere emitting photons at that specific wavelength as electrons cascade down from the third to the second energy level of the hydrogen atom. That emission line, the Balmer alpha transition, is one of the most abundant spectral features in stellar astrophysics. It is the same emission that turns emission nebulae the deep red color visible in long-exposure astrophotographs of star-forming regions. During a total solar eclipse, it becomes briefly visible to the naked human eye as a 1 to 2 arcsecond arc at the moon's limb against the white corona. Prominences may be visible. Solar prominences are large, magnetically confined structures of relatively cool, dense plasma suspended in the much hotter corona, anchored at their bases to the photosphere by strong magnetic field lines and extending tens to hundreds of thousands of kilometers into space. Visually, during totality, they appear as pink or reddish knot-like projections at the edge of the moon's disk, protruding slightly beyond the silhouette. A prominence of average size extends roughly 40,000 kilometers above the solar surface. The diameter of the Earth is 12,742 kilometers. A single prominence can be 3 times the Earth's diameter in height. The moon at the moment of the August eclipse will be at a position in its elliptical orbit that places it near but not at perigee, not its closest approach to Earth. The angular diameter of the moon during this eclipse will be approximately 32 arc minutes and 20 seconds, fractionally larger than the sun's angular diameter of approximately 31 arc minutes and 30 seconds. The moon will completely cover the photosphere with a marginal overlap of less than 1 arc minute. This geometry, the moon slightly larger than the sun in angular terms, produces total rather than annular eclipse. Had the moon been at apogee, its far point from Earth, Its apparent diameter would shrink below the sun's, and the central shadow would not reach Earth's surface, producing instead an annular eclipse where a ring of photosphere remains visible throughout, and totality, with its corona and chromosphere and Bailey's beads, would be entirely absent. The difference between total and annular eclipse is not a matter of degree. It is a binary distinction, corona or no corona, determined entirely by the moon's distance from Earth on that specific date, a value that varies by roughly 50,000 kilometers between perigee and apogee across the lunar orbit cycle. 160 kilometers to the north or south of the central line, totality lasts only seconds. At the edge of the umbral shadow, the geometry collapses and Bailey's beads persist without ever fully closing. The observer never reaches true totality at all, though they may stand in near total darkness with the corona barely visible for an instant before the last photospheric sliver reappears. The width of the path is not negotiable. It is determined by the geometry of three bodies: Sun, Moon, Earth, whose positions are known to sub-kilometer precision centuries in advance. No weather modification, no technology, no decision made by any human institution can alter by 1 meter the boundary of the umbral shadow as it sweeps across the Iberian Peninsula on the morning of August 12th. Every second of totality over Palma de Mallorca will last exactly as long as the orbital mechanics require, and not 1 second more. At 10:24 Universal Time, approximately 2 minutes and 18 seconds after it began, the western limb of the moon will begin to uncover the sun's photosphere. Bailey's beads will reappear. The diamond ring will flash a second time. Shadow bands may ripple again. The corona will vanish back into the scattered blue light of the reopening sky. The temperature will begin rising. The birds will resume their calls. And the shadow, still moving at over 2,000 kilometers per hour, will race away eastward across the Mediterranean, leaving behind a strip of land no wider than a mid-sized country, and millions of people standing in the returning sunlight, looking at the same star they have seen every day of their lives, now briefly knowing it as something other than a source of warmth and agricultural cycles and vitamin D synthesis. Knowing it, for the first time or the 10th, as a star. A specific particular middle-aged G-type main sequence star, one of roughly 200 billion in this galaxy alone, currently fusing approximately 600 million metric tons of hydrogen into helium every single second in its core, and doing so with a precision and consistency so extraordinary that the timing of its eclipses can be calculated to within a fraction of a second from the surface of one of its orbiting planets, using mathematics developed by a species that did not exist for the first 4.5 billion years of its life. The sun will rise tomorrow. That sentence carries a certainty so deeply embedded in human cognition that it functions more as a biological assumption than a conscious prediction. Every nervous system on this planet has been calibrated by evolution to expect it. Crops were planted on the basis of it. Calendars were built around it. Religions organized their most fundamental rituals according to its rhythm. The sunrise is the most reliable event in human experience, and it is reliable for a reason that has nothing to do with divine guarantee or cosmic benevolence. It is reliable because a ball of gas roughly 1.4 million kilometers in diameter, containing 99.86% of all the mass in this solar system, generates enough gravitational authority to hold 8 planets in stable orbits across timescales measured in billions of years. The sunrise is reliable because orbital mechanics is reliable. Because gravity, described by the same mathematical relationships in every cubic centimeter of observable space, does not fluctuate or negotiate. That reliability is itself one of the most scientifically remarkable facts about the universe we inhabit. The laws of physics did not have to be consistent across space and time. There is no a priori logical necessity that the gravitational constant measured in a laboratory in Zurich should equal the gravitational constant operating in a binary star system 20,000 light-years away. There is no mathematical proof that the speed of light measured today should be the same as it was 1 billion years ago. These are empirical observations, verified to extraordinary precision by independent measurements across cosmic distances and look-back times. But they are not logically required. The universe could have been built differently. It was not. And within the framework of consistent physical law, the night sky of 2026 becomes not merely a calendar of curiosities, but a direct readout of that consistency, of orbital periods preserved across billions of years, of light travel times from objects whose distances we can calculate, of isotopic ratios that encode the nuclear history of stars that died before our sun formed. The 9 rare events of this year are not disconnected spectacles. They are expressions of the same underlying physical order viewed from different angles and at different scales. The total solar eclipse of August 12th is a statement about the geometry of 3 bodies. 2 of them formed from the same collapsing molecular cloud, one of them a fragment broken from the young Earth by a Mars-sized impactor approximately 4.5 billion years ago. The Moon's existence is itself a consequence of one of the most violent events in Earth's history. The giant impact hypothesis, now supported by multiple independent lines of evidence, including the Moon's iron-depleted bulk composition, its oxygen isotope ratios nearly identical to Earth's mantle, and the angular momentum of the Earth-Moon system. Without that impact, Earth would have no large moon, and total solar eclipses, in the specific form they take, with a natural disk precisely matching the Sun's angular size, would not occur. The eclipse path crossing Spain on August 12th is traceable, causally, to a planetary collision 4.5 billion years in the past. The major lunar standstill, peaking in 2025 and 26, is a statement about the precession of the lunar orbital plane, a slow nodding motion of the Moon's orbit driven by the combined gravitational influence of the Sun and the equatorial bulge of the Earth. It completes 1 full cycle in 18.6 years. The humans at Callanish and Chimney Rock who aligned their stones to the standstill moonrise did not understand the precession of orbital planes. They did not have differential equations. What they had was time, generations of careful naked-eye observation recorded not in writing, but in stone, in the placement of megaliths on landscapes, chosen with a precision that modern archaeoastronomers can verify with total solar and lunar geometry software. They were doing astronomy. They were doing it without the theoretical framework we now possess, but they were doing it in direct engagement with the same orbital mechanics that JPL uses today to compute spacecraft trajectories to the outer planets. The continuity of that engagement, from Neolithic monument builders to Babylonian scribes recording planetary positions on clay, to Copernicus reordering the geometry to Newton, deriving the force law to Leverrier, finding Neptune with pure mathematics to the Rosetta spacecraft escorting a comet nucleus for 2 years at 500 million kilometers from Earth, is not a metaphor. It is a literal, unbroken chain of inherited observation and inference, each generation building precisely on the measurements and failures and revisions of the one before. Science is not a collection of facts. It is a method of error correction applied persistently across time. The interstellar comet C2025R3 has already begun its departure. By mid-2026, its distance from Earth is increasing by millions of kilometers per day. The JWST spectroscopic data collected during perihelion will continue to be analyzed for years. The full dataset has not been publicly released. The peer review process for the most sensitive measurements is ongoing, and several competing interpretations of the anomalous acceleration profile remain unresolved. Some of those questions will be answered, some will not be fully resolved before the object passes beyond the sensitivity threshold of any instrument we possess. In that respect, the interstellar comet is a precise analog for the broader condition of scientific knowledge, permanently provisional, permanently incomplete, advancing not by achieving certainty, but by progressively narrowing the range of viable explanations. What the detection of 2 interstellar objects within a decade, Oumuamua in 2017, Borisov in 2019, and now C2025R3 in 2025, has established beyond reasonable doubt is that interstellar objects passing through the solar system are not rare in the astronomical sense. They are common. The reason so few had been detected before 2017 is simply sensitivity. Previous sky survey programs were not fast enough, deep enough, or systematically comprehensive enough to find them. The next generation of survey infrastructure, specifically the Vera-C, Rubin Observatory in Chile, whose legacy survey of space and time began full operations in 2025, is expected to detect multiple interstellar objects per year as it scans the full southern sky every few nights to depths no previous ground-based survey approached. The solar system, it turns out, is regularly visited by material from other stellar systems. It always was. We simply lacked the instruments to see it. That realization changes the conceptual boundary between our solar system and the rest of the galaxy. The heliosphere, the bubble of solar wind plasma that extends roughly 100 astronomical units from the sun and separates the solar environment from the interstellar medium, is not an impermeable barrier. It is permeable to fast-moving solid objects, to cosmic rays, to interstellar dust grains. The solar system is not sealed. It is embedded in the galaxy and continuously exchanging material with it on timescales that dwarf human civilization, but are geologically routine. The six-planet parade of late February, Mercury, Venus, Jupiter, Saturn, Uranus, Neptune arranged along the ecliptic, is a visual demonstration of the flatness of the solar system, which is itself a preserved record of the angular momentum of the original collapsing molecular cloud from which the sun formed. That flatness has been maintained for 4.5 billion years against the gravitational perturbations of passing stars, giant molecular clouds, and the tidal forces of the galactic disk. The ecliptic plane today is nearly identical to the original mid-plane of the protoplanetary disk. When you trace the arc of planets across the sky on a February evening, you are looking along the plane of a structure that formed before the Earth existed and has maintained its geometry across a span of time, in which the solar system has orbited the center of the Milky Way roughly 20 times, 20 complete galactic orbits, each one taking approximately 225 to 250 million years. A single galactic year ago, the dominant land vertebrates on Earth were the archosaurs, the lineage that would eventually produce the dinosaurs. 2 galactic years ago, the first complex animal life was just beginning to diversify in the Cambrian explosion. 20 galactic years ago, the sun had not yet formed. The total lunar eclipse of March 3rd, the blood-red moon hanging in the sky above 3 continents simultaneously, that color, that precise shade of copper and crimson, is Earth's own atmosphere rendered visible from 250,000 miles away. The light reaching the moon's surface during totality has passed through every layer of our atmosphere, been filtered by every molecule of nitrogen and oxygen and ozone, scattered and refracted and bent around the planetary limb. The color of the eclipsed moon is a portrait of the air we breathe, projected onto the nearest solid surface in space. If our atmosphere were thicker, richer in aerosols from volcanic activity, the moon would darken toward brown or charcoal. If it were thinner, it would barely redden at all. The precise hue of a total lunar eclipse is a measurement of Earth's atmospheric state at that moment, and it has been changing imperceptibly over geological time as the composition of the atmosphere evolved from the reducing chemistry of the early Earth through the Great Oxidation Event 2.4 billion years ago to the nitrogen-oxygen balance of the present. Every eclipse in Earth's past cast a different color onto the moon. We will never know what color those ancient eclipses were because the moon carries no record of the light that once fell on it. But the physics that governed them was identical to the physics of March 3rd, 2026. The Perseid meteor shower, which will peak in the pre-dawn hours of August 11th and 12th, the night before and the morning of the total solar eclipse, originates from debris shed by Comet 109P/Swift-Tuttle, a periodic comet with an orbital period of approximately 130 years, last at perihelion in 1992. Every year in mid-August, Earth passes through the stream of dusty debris strung along Swift-Tuttle's orbital path, and the particles, most of them smaller than a grain of sand, some reaching the size of a pea, enter the atmosphere at roughly 59 kilometers per second and ablate in a brilliant streak of ionized air at altitudes between 70 and 100 kilometers. The light of a meteor is not the particle burning, it is the air glowing. The kinetic energy of a particle moving at 59 kilometers per second is converted almost instantly into heat and ionization of the atmospheric column it passes through. The particle itself is typically consumed completely before it reaches 50 kilometers altitude. The Perseids on the night before the eclipse will streak across the same sky that, in a matter of hours, will go dark in the middle of the morning. 2026 is not extraordinary because rare things are happening simultaneously by some principle of cosmic alignment or meaningful convergence. There is no such principle. The orbital mechanics that produce the August eclipse, the February parade, the March lunar eclipse, the lunar standstill, the interstellar comet, these processes operate on entirely independent timescales and were set in motion by entirely independent physical events. Their convergence in a single calendar year is a statistical accident. Though given sufficiently long timescales, all such convergences occur eventually, as they have before in Earth's past, and will again in its future, regardless of whether any observer is present to register them. What gives 2026 its weight is not the universe's indifference to human attention. What gives it weight is human attention itself, the 400-year accumulation of instruments, mathematics, spacecraft, and institutional scientific culture that has made it possible, for the first time in the history of this planet, for a species to not merely witness these events but to measure them, to interpret them, to extract from them data about the formation of planetary systems around other stars, the origin of the water in its own oceans, the mechanism by which a star heats its corona to 10 million Kelvin, the chemical inventory of objects formed before the sun existed. The capacity for that kind of attention, recursive, cumulative, self-correcting, did not exist on this planet for the first 4.5 billion years of its history. It has existed in the form we recognize as modern science for roughly 400 years. That is approximately 1/10,000,000th of Earth's age, and in that brief, geologically invisible interval, a species of terrestrial primate has built instruments sensitive enough to measure the isotopic composition of water vapor streaming off a comet from another star system, calculated the gravitational interactions of 8 planets across centuries with sub-kilometer accuracy, and placed a gold-mirrored telescope at a gravitational equilibrium point 1.5 million kilometers from home, pointed at the universe. On August 12, 2026, the moon's shadow will sweep across the Iberian Peninsula in 4 minutes and 31 seconds from the Atlantic coast to the Mediterranean. The umbra will cross at roughly 2,000 kilometers per hour, faster than any aircraft, indifferent to national borders, unaffected by cloud cover directly above the path, slowing for nothing. For every observer in its 160-kilometer-wide corridor who has clear skies, it will last 2 minutes and 18 seconds at the center line, 2 minutes and 18 seconds of direct access to the solar corona, to the chromosphere, to prominences 3 times the diameter of the Earth extending into 1,000,000 Kelvin plasma, to a sky dark enough, for a few seconds at the edges of totality, that the brightest stars emerge in mid-morning. The universe does not offer explanations. It offers phenomena, real, measurable, physically precise, governed by laws that apply with identical authority from the interior of an atomic nucleus to the large-scale structure of the observable cosmos. The sky is not a backdrop. It never was.